I will try to tell you about the imaginary time correlations. It's about the work what was done with my PhD student. And this is the outlook. I will tell you about the extended Bose-Hubbard Hamiltonian. And after that, I introduce the imaginary time correlations, how they looks like, how they appear naturally in some contexts, and how they are connected with the dissipative models. And the last, I think, at the end, I will show you the results. So we start with the Bose-Hubbard Hamiltonian. It contains the three parts. First is the interaction, the on-site. This is the green one. Later, we assume that the particles could tunnel between the nearest neighbor's lattice sites, and you have the chemical potential. And chemical potential is just energy you require to add or subtract particle from the system. So it could be an open system. And in such system, you have two phases. One is the mode insulator. It means that the particles are pinned to the lattice sites, then cannot move. And the superfluid, which is a quantum coherent phase. And this is, we called it superfluid. And this is the result, which shows you that I'm using analytical only calculations. So this is a comparison with the Monte Carlo. And you see that within the numerical error, the results are the same. So the method is very good. It's a quantum rotor approach. So we use that all the time. Which is very good to deal with the systems which are from the many body systems, and when the correlations are important, the size of the system is important, the geometry is important, all of that stuff. So to the basic Bose-Hubbard Hamiltonian, we add the extended version. This is a density-induced tunneling. What this term means? This term tells you that the particle could tunnel to the nearest neighbor only when there already exists some particle. So that's why it's called density induced. So we expect two phases. First one is connected with the condensation, Bose-Einstein condensation, but only with the single particle. And we wanted to see the condensation also connected with the condensation of the bosonic pairs. So you have a two kind of superfluidity of the single particles and the superfluidity of the pairs. So how to know that you have that? We expect this lambda peak in the specific heat, which is very famous, and it distinguishes and it shows you how the energy is absorbed by the system, because the specific heat means that you observe fluctuations. And you have really look into that if you want to see those phases. So you made the calculations using the path integrals method. In which obviously you have to split the first term because it's non-linear. The interaction is non-linear, you have to split it. The cost of the splitting, and you have to provide additional field. This field could be static, like in the mean field, or Matsubara time dependent. And this is the key point. Immediately you see that something like a pairing appears in that model, but you have to put a lot of effort to change the variables to the phases, which are low energy excitations. And finally, you got the U1 phase model, and you see the two terms which are important. It's the cosine phi, it means tunneling single particle tunneling, and the cosine 2 phi means that both particles tunnel at the same time. We calculated the specific heat, and you could see two lambda peaks. The first one is connected with the basic BEC condensation, and the second one is responsible for the pair condensation. So we have two-phase system. It seems that in that conditions, what we could see that this additional term, density tunneling term, improves the temperature of the original BEC condensation. But when you compare it with the experiment, It's quite opposite. So we started to think that something is wrong with the theory, but nothing is wrong actually. So we decided to do what is called in the condensed matter physics, the coupling between the system and the buff. And this usually it was used by Caldera and Leggett in the context of Josephson junction arrays or the rest of that. You could couple a system with the environment. And it could be a thermal, bias, whatever you wish. But this is artificial. The coupling means that the surroundings interacts harmonically with your system. But still, this is artificial. So we started to think if we need any of that. And actually we don't. And those are dissipation terms which comes from the imaginary time correlations. So once again, we start with the Bose-Hubbard Hamiltonian. We add the density interaction term, and we use a path integral method. At some point, you have to calculate the trace of the correlations. So you get the correlation function, which is a g, and now you could expand it because you need integrate once again. So you have to expand it in Taylor series. The Taylor series contains some parts which are imaginary, and usually you just cut it off and you say, okay, it's imaginary, so it's not very important. So for the first time in that man-body physics, we started to think, okay, maybe it's not. Maybe we need it. So we split our grid function for the part which depends on the imaginary time, and it does not. And we once again calculated the action, and we see again, once again, the same parts. I mean, cosine term, which is responsible for the single particle tunneling, and this 2 phi cosine term, which reflects the fact that both particles could tunnel. But now the amplitudes depends on the Matsubara time, but you can sum over it and get a real result. So it looks like we have a trivial difference because at the end we've got the same partition, the same correlation function in both cases. When we couple the systems artificially and if we use the imaginary time correlations. There are some differences. So we thought that maybe it's not so important if those terms, if we couple artificially or we just do the imaginary time correlations. But when we look at the results, actually it's something totally different. So those are phase diagrams, and what you see is the transition between the superfluidity and the Mond insulator phase. BAF is artificial coupling. Imaginary time correlations are just blue frame. So at the beginning, everything looks okay. So the system goes into the superfluidity eagerly with the density-induced tunneling, then alone. But at some couplings, you see that unfortunately for the artificial coupling, there is a gap when there is no superfluidity at all. It's some strange phase. We called it incoherent phase, but incoherent pair superfluidity, something like that. What you see more is a cutoff. The cutoff in the BAF approach does not depend on the density. And you do not expect something like that when you add the term which is called density induced term. So it means that this approach cannot catch the critical properties of the system properly. It is worth to consider because it's an easy part, because you have a harmonic coupling between two systems, the system and the buff, but unfortunately you cannot get any critical behavior. And this is very bad for the many-body physics, where you cannot just create one particle system, two particle system, three, and add, and in the end expect that everything what has just happened in the small system is going to happen with the many-body system. It's not going to work. We also did some Taylor expansion of the green function, and what we see is that our results are in very good agreement with the imaginary time correlations. So this is a line which shows you that the actually density of the particles governs the behavior, the critical behavior of the system as expected. This is the line from the imaginary time correlations. It's almost the same. This is from the critical line equation, not from the Green's function. And this is just the buff. So it means that it actually didn't catch the properties of the system properly. So the message to take home is that, in my opinion, the theoretical physics is about the mathematics and applying it to the artificial systems. Of course, those days we need immediate results to publish, but when you wait long enough, sometimes 100 years, then you reach the goal. And the last one, using these imaginary time correlations, we describe the system more fully, comprehensively. We don't need any kind of decoupling. We don't need it. The coupling appears there just naturally because of the calculations. So thank you very much.
Thank you very much for introducing this new concept to us. So we have time for questions at the end of the day. Yes.
Just curious, like because Caldera or something, that kind of model really feels like artificial, although interesting. So like, I really like to learn from you, like what is this ITC? But would you like
I haven't catch the first phrase, what you said at the beginning.
Sorry, like just I agree with you that there are some artificial couplings that.
Okay. You mean that because of the procedure, you could get something which is artificial, and maybe it's just the way that it appears. Yeah.
Yeah. We do not know what the natures really is, whether they are really harmonic beds or not. It's kind of artificial.
Yeah. I mean, when you start the procedure with the Hubbard-Seltonovich transformation, also appears some imaginary terms, but those terms are throughout by the gauge transformation. You have to do also the gauge transformation, which these artificial terms just going out. And those what's left, it's actually imaginary time correlations. So because the gauge, you could use whatever you wish, yeah? So you look at the terms which are not the sources, not the fields, not something like that, and you just throw them out using the U1 transformation, because the theory is invariant, and then the U1 transformation because is the phase theory. And the phase could repeat itself after 2 pi. So that's what we do. That's what we know, that it's not some artificial or strange part which just appeared because of the transformation.
Thank you.
Yeah.
Some other questions? Everybody's very tired, but we have time. Everybody stayed perfectly on time. I very much like the ending about what theoretical physics is all about, and I agree, although with a small addition that theoretical physics also has to create the model that.
Yeah, I agree.
Okay, let's thank all our speakers of this session once again.